Good morning, everyone. First of all, thanks to the organizer for this wonderful meeting during these very difficult days around the world. My name is Marisa Frechero. I am from Bahía Blanca, Argentina. I am professor at the Universidad Nacional del Sur and senior researcher at CONICET. In this talk, I'm going to present our development of a new hybrid glassy material for electrochemical green energy storage. This is the outline of this talk, where the main topic are lithium and glassy materials. Today, to change the energy paradigm in South America needs to overcome many barriers: social barriers, political barriers, industrial barriers, and many others. As scientists, we have to provide information and new develop on low-cost and environmental-friendly technology. Because today humans need energy for everything, for very different things, and in a very different scale. Then we need to accumulate as much energy as we can. In Argentina, we have the largest reservoir of lithium. Because of that, the use of lithium is a hot topic research for us. Today, almost the whole exploitation of our lithium is exported as a raw mineral. In the lithium universe, lithium batteries are the stars. Lithium batteries are in the market since 1991. However, they are still waiting for a better performance. They are affected by several technical issues like chemical stability, thermal stability, and also structural stability. We have to do much effort to explore new solutions for such problems. The thing is that new designs are becoming less common. Yes, we'll still use the voltage model. Taking into account that the next generation of batteries are the solid-state batteries, due to many reasons, but probably the most important is safety, the main problem to solve is the interface between the electrode and the electrolyte. What we really need is to remove the doors to facilitate the ion moving, and then what we have to build is better contact between those materials. Ions need to move fast and easy inside the material, and such movements have to avoid a large structural change to minimize the mechanical damage. To find a good material to use as electrolyte, it's necessary to satisfy a list of requirements, like a large amount of mobile carriers with a low activation energy in a highly polarizable skeleton. Also, it is needed a material with chemical stability, lightweight, low cost, cheap, and friendly with the environment. However, almost 90% of the reported potential materials have never been tested in real batteries, and they don't satisfy one or more than one properties in this list. Almost 10 years ago, we already have a long list of potential materials for electrolytes, but many of them don't have a good performance in the appropriate temperature range. Between 60 to minus 20 Celsius degrees, because they have low conductivity or large activation energy. Or worse, They are too expensive and not green. Then we bet for glassy materials, because they have almost every property listed before, and added to that, they are easy to prepare, only mix and bake. They are isotropic and easy to modify also. Quenching method is the most popular to obtain glasses in a large industrial scale, and it has a good reproducibility. As you can see in this picture, glasses formed with many different oxides are obtained just finding the correct cooling rate. One of the greatest glasses matrices obtained in our lab was a phosphate glass modified with bismutate and barium oxides. This glass is particularly non hygroscopic, and it is able to contain a large amount of lithium oxides, lithium cations. As you can see in this plot, a high conductivity at moderate temperature is reached, with a low activation energy also, and is a very good glassy material, as you can see at the picture on the left side. Then, considering how promising is this glass as electrolyte, we studied its aging. Aging is something that needs more attention because many times great materials don't resist along the time and cycles in batteries. We put our glass through a different overheating processes near to its glass transition temperature, and we analyzed how reliable its structure was, how it affected its conductivity through these periods of overheating. We found that after a few hours, some crystallization appears, as you can see in the pictures on top. Also, some cracks on the surface, as you can see in the pictures above. Then, its structure stability is only affected if the overheating is near its TG. Also, its conductivity, which diminishes over the time overheating. Now, inspiring Soggy-sand materials, which were created to avoid or to diminish the grain boundary problem of ceramic conductors, and were designed by the combination of inorganic particles with ionic liquids that confer a favorable path for ionic migration over the crystalline surfaces, we developed our hybrid glass. Our hybrid glass is formed by the combination of an improved version of our phosphate glass, where the barium oxide was replaced by magnesium oxide to obtain a lighter and greener glass. With the ionic liquid ISyDMA’5 that has a high viscosity, we obtain a very good solid electrolyte. First, we studied the electrical response without the incorporation of extra lithium salt, considering that our glass already contained mobile lithium ions. The result, as we can see in this plot, is that the conductivity is higher than the naked glass, but almost independent of the composition of the glass as substrate. Therefore, we are testing the electrical response only the ions that can release from the glass and moves along the grain boundaries. We also show here that depending on the glass composition at the substrate, the hybrid conductor could resist up to 300 Celsius degrees before a degradation, before to lose oxygen. But the most outstanding result of this hybrid glass conductor is that with this material, we can obtain a flexible film, avoiding the use of a polymer. Now, what are we doing now? We are exploring how much salt, lithium salt, or maybe another cation salt can be added to this hybrid. How much its ionic conductivity could be raised, and, of course, how its chemical and mechanical stability is affected by the use of different salts. I mean, inorganic salts or organic salts. How different the ion mobility could be according to such different salts, glasses, or different ionic liquids. Unfortunately, a very precise selection of material, for electrolytes or electrodes, is not enough to guarantee a good functionality of a battery. Then, the biggest challenge is to find the best couples, electrode-electrolyte, to improve the interface between them. Because of that, we test our materials through the assembly of small solid-state batteries, like in this picture. But this is for another talk. Finally, through this contact, you can send me any question. And now, to end this presentation, I want to say thanks to the members of my group, who work every day at the lab with a great passion, and of course, now to say thank for your attention in this talk. Thanks, and keep yourselves safe of COVID.